Welcome back. Over the last 4 lessons, we built 12 clipper variations. Each one used a single diode and at most one DC source. That means each circuit could only clip at one level. Either the positive peak was cut or the negative peak was cut, but never both at the same time. Today we ask, what if we want to limit the output on both sides? The answer is simple. We place 2 shunt branches in parallel with the output. Each branch has its own diode and its own DC source. One branch clips the positive peak, the other clips the negative peak. This is the double source clipper, also called a 2-level limiter. Here is the circuit. The input sine wave goes through a series resistor R to the output node. At that node, 2 branches connect down to ground. The first branch has diode D1 in series with battery VDC1. D1 is oriented so that it conducts when the input is sufficiently positive. The second branch has diode D2 in series with battery VDC2. D2 is oriented in the opposite direction, so it conducts when the input goes sufficiently negative. Each branch works independently. When the input is in the middle range, both diodes are off, and the output simply follows the input. Let us find the 2 transition voltages. For the upper branch, set the current to 0 and the diode voltage to 0. Kirchhoff's voltage law around the upper shunt branch gives the transition voltage VT1 equals plus V1. When the input exceeds plus V1, D1 turns on and the output locks at plus V1. For the lower branch, the same method gives the transition voltage VT2 equals minus V2. When the input drops below minus V2, D2 turns on and the output locks at minus V2. Between these 2 levels, both diodes are off and the output equals the input. So the circuit creates 3 distinct regions. Region 1, input above plus V1, output locked at plus V1. Region 2, input between the 2 transitions, output follows input. Region 3, input below minus V2, output locked at minus V2. Here is what the output looks like with an ideal diode. The input is a 10-volt peak sine wave. Every time the sine rises above plus V1, the output flattens out at plus V1. Every time the sine dips below minus V2, the output flattens at minus V2. In between, the output traces the original sine shape. The result is a sine wave with both peaks clipped off. The output is trapped inside the voltage window from minus V2 to plus V1. If V1 does not equal V2, the window is asymmetric. Now let us add the silicon diode drop. In this example, VDC1 is 3 volts, VDC2 is 2 volts, and each silicon diode has a forward voltage VD of 0.7 volts. The upper transition becomes VDC1 plus VD, that is 3 plus 0.7, which equals 3.7 volts. The lower transition becomes minus the quantity VDC2 plus VD, that is minus the quantity 2 plus 0.7, which equals minus 2.7 volts. So the output window is from minus 2.7 volts to plus 3.7 volts. Notice this is asymmetric. The positive clip-in level is 3.7 volts above 0, but the negative clip-in level is only 2.7 volts below 0. If you wanted a symmetric window, you would set VDC1 equal to VDC2. And with that, the clipper series is complete. We covered 13 variations across 5 lessons. Series simple clippers with the diode in series. Series biased clippers adding a DC source in series. Parallel simple clippers with the diode in the shunt branch. Parallel biased clippers adding a DC source to the shunt branch. And finally, the double source clipper, combining 2 branches for 2-level limiting. The key method was always the same. Set the current to 0, set the diode voltage to 0, and find the transition voltage. Next topic, clamper circuits. Instead of cutting off peaks, a clamper shifts the entire waveform up or down without changing its shape.